I'd like to thank you for inviting me to give this presentation. I'm sorry I couldn't be there in person, but hopefully this video works out for you. Today, I'm going to talk to you about a project that I've been working on for about the past 3 years, developing drones for mosquito control. Specifically, I'm going to discuss a device that we developed to autonomously drop larvicide briquettes from a drone. This is our custom-built drone. It's a hexacopter, 6 motors, 6 props, and it's powered by 2 large lithium batteries. It was built with 90% off-the-shelf parts, but those parts were hand-selected to give us the required flight characteristics, namely the ability to lift a heavy payload and give us a long flight duration. This machine can lift several pounds and can fly for about 35 minutes without a payload, less time depending on the weight of the payload. It weighs about 13 pounds total and cost about $5,000 to build. Now it's controlled by a small onboard computer or flight control system with a whole host of sensors that enables this machine to fly completely autonomously without any input from the user. It's controlled with a tablet. This is a screenshot from the Android tablet we use to program the drone. You simply outline the area you want to fly with your finger, like so, and the software will automatically generate the required flight path. Then you send the mission to the drone by radio link, press go, and the drone will take off, fly the mission, return the sprayer on and off, return to home, and land all by itself. You do not need any special experience flying RC vehicles to fly this drone. I can teach anyone to fly it in about a day. We've developed several modules to cover every aspect of mosquito control that we could think of, but primarily we focused on larviciding. This is our liquid larvicide sprayer applying Vectobac 12AS over a salt marsh to control Aedes sollicitans. You can see the sprayer here underneath the drone. It has 2 T-jet agricultural nozzles that allow us to select any application rate, droplet size, or spray pattern that we wish. We've done a lot of testing with this unit and we really have it dialed in. Here's a sample spray card that we placed on the marsh during one of our tests. You can see we're getting excellent coverage of the area. We're putting out about 200 micron droplets and getting those drops on the ground at the desired application rate. Unfortunately, we've gotten mediocre results, about 30 to 50% control, despite applications under best case situations, right before a full moon high tide and a rain event that should have washed the material into the mosquito pools. But this isn't really unusual for liquid larvicide products applied by air, which is why many mosquito programs prefer to apply solid materials, my own program included. So we decided we needed to develop a mechanism to apply solid larvicides. The first decision was, did we want to design for granules or briquettes? We settled on briquettes because from an engineering standpoint, it was an easier problem to solve. We just need to get the briquette to drop to the ground versus granules, which need to be applied evenly at a specific application rate. Also, I just had a better vision in my head of how the briquette unit would work. Then we needed to decide which briquettes. We looked at a number of options, but settled on Natural XRT briquettes, mainly because they're nice and thin, so we could fit a bunch of them in a small space. They also looked like they dropped straight down because they're relatively heavy and skinny. And we actually confirmed this by dropping a bunch off the roof of our lab. Not only did they drop straight down, they also survived the drop without breaking. So once we knew what briquettes we were using, I sat down and used some 3D drafting software to design the unit. Now, I apologize for this slide. This was supposed to be an exploded diagram of the unit so I could show you exactly how it's constructed and operates. But we've actually applied for a patent on this device, and our Office of Technology has said, no, you can't show that. So unless everyone in the room wants to sign a non-disclosure agreement, we've got to keep the how this works a secret for a little bit longer. But I will show you the device in action. The entire unit, with the exception of the electronics, was printed in-house on our 3D printer. This allowed us to create prototypes very quickly and very inexpensively. Here's the base of the unit, still on the printer right after it was finished. We went through about 3 different designs. The final version holds 7 natural briquettes, but we could reprint the device to drop any type or number of briquettes that we want. Once we had a working unit, it was time to test it. This is a large athletic field where we did our testing. We selected 4 target sites on the field indicated by these X's, 1, 2, 3, and 4. They're spaced 50 feet apart this way and 100 feet this way. We programmed the drone to take off. Here is our starting point. Take off, fly about 13 feet above the ground to each site, pause for a few seconds to give it time to stabilize, drop a briquette, fly to the next site, and repeat. And then at the end, return to home and land. These green lines represent the actual flights as recorded by the flight control system. The horizontal lines are the flight path and the vertical lines are the altitude. While the drone was running the mission, I followed behind and placed flags where the briquettes landed so we could measure how far we were from the target site. And we replicated this test 3 times. This is a video of one of those replicates.
Okay, we're running flight 3, actually dropping.
So you can see the drone flying to the first site. Now it's going to pause, drop the briquette,
Practically
and I've placed the flag. And I really need to get my cameraman a tripod. Site 2. You can see I try to stay a safe distance behind just in case. And now you can see the unit here in red. It's about the size of a coffee can. And now a good close-up view of the unit.
going on.
And now it's flying back home to land. So you can see the unit functions just perfectly. This image shows the results for all 3 replicates. The yellow hexagon represents the target site. All the other spots are where the briquettes landed. The different colors are for the different sites. Red is site 1, green is site 2, blue 3, and purple is site 4. The shapes correspond to the different replicates. And here is the scale, 10 inches. What we see is on average, the briquettes landed within 45 inches of the target. Now this is pretty good. The drone is using GPS to find the targets, and the typical accuracy for GPS is 7 to 16 feet. And we're landing within 4 feet of the target, so we're pretty happy with that. The other thing to note is that the accuracy and the precision increased as the mission progressed. So here's the first drop in red. You can see the spots are far from the target and far from each other. But by site 4, you can see the drops are closer to each other and closer to the target. This was a significant trend with an R-squared value of about 0.95. So why did we do better at the end? Well, maybe we had a better GPS signal on that part of the field. Maybe the drone just had more time to fly and adjust its flight path. I'm not really sure, but the longer we flew, the better we did. Now, while we were really happy with those results, we wondered if we could do better. Can humans get better results than a computer? Could we hit, say, a bird bath in someone's backyard? So we set up another trial. We placed 4 5-gallon buckets out at the target sites. And if you look closely, there's 1, 2, 3, 4. And they're just regular Home Depot buckets with a 12-inch diameter. And here's our drone over here. We attached a wireless high-definition video camera to the bottom of the briquette unit. Then I flew the drone manually using this transmitter. And when I got close to a bucket, I would tell the drone to hold its position. Then I could look through these high-definition goggles and ease the drone over the bucket and drop a briquette by flipping a switch on the transmitter. And here's a video of one of my attempts. Position hold, easing over, and bingo, we got it. And that was my very first attempt. I got lucky. They didn't all go that perfectly, but even when I missed, it wasn't by much. We usually landed just outside the bucket, and with practice, I'm sure I could do even better. So manually, we're able to hit a 12-inch target, much better than the 4 feet we were getting with GPS. So what's next for this project? I'd like to look at other briquettes. Alticid has a Canadian version of their XR briquettes that are much smaller than the ones we typically see, about the size and shape of a Kit Kat bar. I'd like to design a unit for those so we can carry more briquettes. Our GPS unit only receives signals from US satellites. Other GPS units combine signals from US and Russian satellites with a GLONASS system. More satellites may increase our accuracy. I want to add an optical sensor. Right now, the drone holds its position based on GPS signals, and therefore the position will vary with the error in that GPS signal. An optical sensor uses a video lens to hold its position by locking onto pixels that it sees on the ground. And if those pixels start to move out of view, the drone will adjust accordingly. This would make manual applications much easier. Most importantly, we want to incorporate RTK GPS. RTK stands for real-time kinematics. It uses 2 GPS units, one on the drone and one fixed on the ground. This increases the accuracy of the triangulation and decreases the GPS error from 7 to 16 feet down to 1 to 2 inches, meaning that potentially we could hit those buckets completely autonomously. I'd just like to thank the Northeast Mosquito Control Association, especially the awards committee that gave us the McColgan grant that made this work possible. Sorry I can't be there to answer any questions, but feel free to send me an email and I'll get back to you. Thank you.